Hi, folks. Welcome to chapter 7, lecture number 4. And we will be having after this another lecture in chapter 7. Today, I'm going to talk about a very, very interesting equipment, test equipment known as impulse voltage generator. We have been talking about the transient over voltage traveling waves. Transient over voltages last very short, as you have learned, and there are two types of transient over voltages: lightning and switching. Lightning is a very, very fast wave. It's just a wave. It's like a pulse, and it travels like a pulse, and it affects the insulation wherever it travels through. Let it be insulators on the transmission lines, let it be when it reaches substation. Mostly the first equipment is the transformer, which becomes very vulnerable, and other equipment in the substations are concentrated number of equipment, number of apparatus are installed at substations, and when impulse voltage, any type, lightning or switching, reaches the substation, when you design the insulation there, we must ensure that the magnitude of the impulse voltage reaching there does not damage in any way the insulation, and that is why you also learned BIL and SIL, the basic insulation level and switching insulation level importance there. So an impulse voltage generator we need to produce the impulse voltage or a pulse like voltage, and there are two: lightning and switching. We'll first learn how do they look like. I think I have already talked about it. As you can see on this slide, the shape of a lightning impulse voltage is being shown here, and this is by IEEE standard, IES, International Electrotechnical Commission, standard 6060, high voltage test techniques. If you ever want to refer, just click on it and you can get the full detail. But it is interesting how the lightning impulse voltage is defined. The purpose behind defining or making so much of effort to define the lightning impulse voltage is, in the earlier days, the oscilloscopes were not developed so well. So, to ensure the shape of the standard shape of the voltage being produced, you must see you must record the voltage wave, pulse wave on an oscilloscope screen. And this voltage being so fast, it was difficult with those old oscilloscopes to even ascertain where does the impulse voltage begin. That means the zero level of the, it was very difficult to ascertain this earlier. And I have come across people in the olden days when I am looking at the oscilloscope through a gadget. I'm able to locate the pulse when I ask any one of some of my colleagues, and the pulse is produced where it is not being stored. You cannot imagine. They have not been able to identify the pulse because it's so fast. It comes and goes. Unless you store it, the storage oscilloscope even came much later. So how it is defined, as you can see the impulse voltage is given always as a ratio T, let's say T1, sorry, T1 by T2. That is the time required to reach the peak value, and the T2 represents the time required to decay to its 50% magnitude, highest magnitude. So as you can see here, this is 50% of the magnitude, and this dotted line is given here. So T2 limit is here. This is the T2 limit, and it is taken, T2 is total time of the pulse duration, because there is a vast difference between the time to reach the peak and decay to 50% value. So because the wave shape is, in this case, lightning impulse, is standard wave shape is 1.2 oblique 50 microseconds. So 1.2 is not that crucial. So total time has been taken. T2 is total time, right from the beginning till up to 50% decay. The 50% decay time to be measured is not that difficult, but 0 is difficult. So where does it begin? Between points A and B on this schematic of the wave shape, a tangential line is drawn, and where it meets the time axis, from there to the 90% of the peak value. This is 0.09. 0.09. So 90% of the peak value, when it reaches that time, because sometimes to define exactly the peak value is also difficult. So from, say, about 10% to 90%, that time is taken to be the rise time. And decay time, we have when it decays to 50% of the peak value. So this is how the lightning impulse is defined. On this slide, you see another pulse. There are some requirement to produce or to apply on a test object a chopped wave. What is a chopped wave? When the 50% decay is not let reach, and before that the breakdown takes place. In the first diagram, as you see here, there is no breakdown taking place at all. You can produce a breakdown. You just simply take an air gap, set the gap distance between two spherical electrodes, and you can produce a breakdown in air between the two spherical electrodes at a desired value of the voltage. So the setting is such that the complete decay of the waveform is not able to take place, and before that, before it reaches the 50% magnitude of the peak value during the decay, there is a breakdown in the air gap, and that when breakdown occurs, you can imagine the voltage falls immediately to 0. Here some finite magnitude of voltage is there, and it reaches zero value. A breakdown also always equalizes the potential, the high voltage to the ground potential, you can say. So this is a chopped wave, and there are requirements by certain gadgets to apply not the full wave but also chopped wave, or you may like to produce chopped wave for some research purpose. TC here, as you can see, TC is the uh, time to crust. It is known as time to crust. That means and you can say uh, actually it is crust means the peak value. In this case, the total duration of the uh, pulse uh, remaining as high voltage is being given as TC. So there, that means the breakdown takes place somewhere between the peak value and the 50% value. In the wave tail, yeah, you must also learn the rising time T1 is known as the wave front time. T2 is known as the wave tail time. So you can say in this case the wave tail time is shortened, is not there because it is not reaching its 50% value. So the total time duration of the pulse is being given as Tc, let's say. So this is wave tail, as you can read it here, and this is wave front, as you can read it here. Wave front and trail, uh, wave tail are defined in this way. Yeah, we had learned earlier also the switching impulse voltage as compared to the lightning impulse voltage is much slower. The wave front and wave tail time as standardized by IEC, as you can read it here, are there are three standard wave shapes for switching impulse voltage: 100 by 2500 microseconds, 250 by 2500 microsecond, and 500 by 2500 microseconds. As you see, the wave tail time, that is the time required to decay to the 50% of the peak value in the standards, is equal, that is 2500 microseconds. But the wave front time has been varied from 100 to 500, 100 to 50, to the 100, 250, and 500 microseconds. In fact, every time a switching operation takes place, the the switching transient produced may have different wave shape. And it all depends upon the instant of switching. It depends upon the circuit conditions, the inductance and capacitance of the circuit, etc. That is the impedance of the circuit, you can say. And therefore it changes every time. So, but for when you want to test an object, you must define the wave shape. So these are the three wave shapes recommended for uh, producing switching impulse voltage in the laboratory. Yeah, one very important thing I did not talk about, there are some tolerances given also in case of wave shapes. In case of lightning impulse, as you can see it again, the T1, there is a tolerance of plus minus 30%. T1 is very small, 1.2 microsecond for lightning impulse wave. So there is a tolerance of the order of plus minus 30% permissible. And for the time when you produce the standard wave shape in the laboratory, that is. And for T2, the wave tail time, a tolerance of plus minus 20% is permitted in case of lightning impulse wave shape. Then we go to switching impulse. You know, as it is given here, T1 or the TCR is the time required to reach the crest, the peak value. Tolerance of plus minus 20% is there, whereas in the wave tail time, a tolerance of plus minus 60% is permissible. Even the laboratory, to produce the exact wave shape is difficult. We'll learn about it very soon. So specifications must give the permissible tolerances in the wave shape. When you have a tolerance in wave front and wave tail time, that means the wave shape tolerances are there. Yeah. Yeah, something very interesting, as you see here, the lightning impulse wave 1.2 by 50 microseconds. So you can say its total duration is in microseconds. But when you convert the switching wave shape into say milliseconds, this will work out to be 0.1 by 2.5 microseconds, isn't it? This will work out, if we do it, 0.1 by 2.5 milliseconds. And the other one, 250, then it will be 0.25, and third one 0.5 oblique the same 2.5, same 2.5 milliseconds. So you can say the duration of the switching impulse voltage wave shape, you can say it is in milliseconds, whereas the lightning impulse voltage wave shape is in microseconds. So there is a vast difference, at least if not 1,000, you can say there is a difference of 100 times the speed, you can say, of the rise and fall of the voltage. So it is, you can say very easily that lightning is 100 times faster wave shape as compared to switching. It is very interesting to note that when you measure the breakdown strength of any dielectric, for which type of wave shape will it be more, for the faster wave shape or the slower wave shape? Give a thought. Obviously, for a faster wave shape, the dielectric strength or the breakdown strength of a dielectric is much higher as compared to the slower wave shape. So you can imagine, even air, when you take a dielectric, it will give you much higher breakdown voltage for lightning impulse switching, lightning impulse shape transient voltage or lightning impulse, as compared to the 100 times slower switching impulse wave shape. When you apply the breakdown strength of air, even reduces. So breakdown strength of any dielectric is higher for the faster wave shape as compared to the slower wave shape. This you must always know and learn. on your life. That's important. And accordingly, the when we design the insulation level, accordingly it has to be designed. And that is the reason you can say, yeah, we have learned uh, also that the BIL and SIL. BIL is the basic insulation level that is applicable till up to a rated voltage of 400 kV. But beyond 400 kV, we have already gone much beyond 400 kV in transmission lines, and transformers are also needed there. And so at so many places uh, for mainly for transmission purpose, beyond 400 kV up to 800 kV AC, and we have gone 800 kV plus minus DC, and 1150 kV transmission line voltage is also being practiced. So when you go to such high level of transmission lines, the significance of lightning impulse voltage pacifies. I mean, is not so much there. Significance of switching impulse voltage increases. We have been talking about it. The reason, the highest known lightning impulse voltage produced on the transmission lines, the insulation level up to 400 kV, or say at 400 kV and above, or say above 400 kV, is able to bear, is able to take care of the maximum lightning impulse voltage magnitude. But the switching impulse voltage is produced as a function of, you can say, depends upon the rated voltage of the system. When the rated voltage of the system increases, the magnitude of switching voltage also increase proportional to the rated voltage. At 800 kV, it would be 800 kV divided by root 3 multiplied by 2, 3, even more than 3 sometimes per unit. Per unit value is rated voltage divided by root 3, that is U naught. The concept of U naught we have already learned. I'll just write U rated is equal to or U rated by root 3 is equal to U naught. This is the voltage between the high voltage conductor and the ground, isn't it? And the switching impulse voltage is something of the order of 2.5 to even more than 3.0 of this value. So as U naught increases or UR increases, the switching impulse voltage magnitude also increases. But lightning impulse, it depends upon the nature, and the highest lightning impulse voltage produced or known is taken care of at level of insulation, basic, we can say basic level of insulation provided to the network above 400 kV, and that is why it is termed as SIL, the switching impulse level of the basic insulation level provided to the network. So importance of switching impulse voltage increases when we go beyond 400 kV. Yeah, let's talk about this just a minute. Yeah, let's talk about the impulse voltage generator. As I said, it's a very interesting, very simple, and very interesting gadget. which produces impulse voltage in the laboratory. Impulse voltage generators are installed in the laboratory, and maybe also sometimes in open air laboratory they are installed, and they are used only for testing the insulation provided to the gadget or to the apparatus by impulse voltage. When the concept of impulse voltage generator manufacture came up in the early 20th century, the knowledge about the switching impulse voltage generation was not there. Maybe it was not needed at that time, because the level of voltages prevalent in the power system network all over the world were very small. Even in 1950s, 220 kV was a big voltage. It was in late 60s that 220 kV was surpassed to 400 kV and all that. And now today we have much higher voltage. So the maximum transmission voltage in the world used to be much smaller. For that, the importance of lightning impulse was very much there, because the lightning impulse, the maximum magnitude of lightning impulse voltage produced was so high as compared to the basic insulation provided to the system below 400 kV. So the lightning impulse voltage was very important thing. It is important today also, but as I said, beyond 400 kV, it is not that significant as compared to the switching impulse voltage. So the earlier generators, impulse voltage generators, were designed to produce only the lightning impulse voltage. But today in the world, a lot of importance to switching impulse voltage wave shape, as we have already defined, the generation of uh, generation of impulse voltage or impulse voltage generators which can produce switching impulse also has picked up. The highest magnitude of lightning impulse voltage in the world, known to me at least, is to the order of 7200 kV. Can you imagine? 7200 kV lightning impulse voltage just can be produced by an impulse voltage generator in the laboratory. And when the importance of switching impulse came up, for switching impulse voltage up to 500 kV, 5000 kV, sorry, up to 5000 kV, 500 would be very small. Up to 5000 kV, the switching impulse voltage generation has picked up. It is slightly tricky and slightly difficult to produce switching impulse voltage in the laboratory as compared to the lightning impulse. And the gadget will learn on what components of the gadget, that is impulse voltage generator, it all depends upon. We'll learn in detail today. So as you see, the basic circuit of generation of impulse voltage or a pulse of certain duration, that is just in the form of pulse is produced. The capacitor C1, as you see here in this circuit, C1 is the charging capacitor. C2 is the load capacitor. This is the load capacitor, as you can see here. We have two resistors, very simple, two capacitors and two resistors. Wave R1 is the wave front resistor and R2 is the wave tail resistor. That means R1 determines the duration of time of wavefront, as well as R2 determines the decay, that means the time required to reach the 50% of the peak value, and that is the tail time. What else is here? You need a source of voltage, and this is a DC voltage. Mind it, you charge the C1 with a DC. And what else you need? You need just a sphere gap. What is the purpose of sphere gap? That's very important. We have learned if the gap distance between two spheres is not very large, that means if the gap distance is up to the radius of the spheres, not greater than radius of the spheres, the field is very much weakly non-uniform. In fact, it is even for up to the diameter of the gap distance up to the diameter of the spheres, the field is weakly non-uniform. And under uniform as well as in weakly non-uniform field conditions, when this is all put in air. Nowadays, some changes have come up that this is enclosed in SF6 gas chamber, but so long, and even today, mostly the sphere gaps are in air. So, for a specific gap distance between two spheres of a specific dimension, the breakdown in air would always take place by application of the same voltage, and that is what is required in this circuitry. So what happens that C1 is charged slowly with DC. The charging capacitor C1 is charged slowly with DC source until the spark gap G breaks down. That means when you have set, you have to set the gap distance between the two spheres at G to the desired level, so at which you want a breakdown in the air. And as soon as the breakdown takes place, breakdown is like a short circuit, isn't it? So the charging capacitor discharges over R1 and R2 on the capacitor C2 that is formed by the load or the test object. C2, as you know, we are always testing the dielectric, and dielectric forms a capacitor, a capacitance forms capacitance. So that is what is under test. So the voltage, you can hold the voltage at C1, and you can also do that, you reduce the gap distance from a longer one to smaller one between the two spheres, and at a certain gap distance the breakdown will take place depending upon what charging voltage to C1 you have applied. Or you can also do that, you fix the gap distance between the spheres and you increase the voltage applied to C1 gradually till it discharges. That means a flash occurs at the gap distance at G. As soon as the flash occurs, the capacitor C1 would discharge, and the flash will not remain for too long. It just comes and goes. So the charge stored in C1 will discharge on C2, and the shape of the voltage produced under this condition, we learn how the shape is produced, or how can you determine the shape to be produced by uh, dimensioning R1 and R2. Now you see here three circuits. A is the normal circuit, and A is a wave shape network. Uh, the as you can see, you in the B circuit, as you can see that in the B circuit, as you can see, what is the difference between A and B? Only the position of R2 has been changed. In B, the R2 is before R1, and in A, R2 is after R1. Now, what do you think? Which of the circuits or connection of R2 would be more efficient? That means we'll have less of losses in the circuit. When we say losses, we are worried about the real power loss, you can say. In R1, the uh, R1 and R2 are working like a potential divider circuit. You must have learned how to divide the potential. You must have made a number of calculations. In the position in circuit A, or in the connection in circuit A, R1 and R2 are making are working like a potential divider. So whatever voltage is coming across R1 is getting divided to some extent by the position R2. So there will be a potential divider which is not desirable. That means potential divider means the output voltage is in between R1 and R2, as you can see in the A circuit. So the voltage is divided. So not full voltage coming is being impressed upon C2, the test object. So to avoid that loss of power or potential, you can say, the position of R2 has been brought before R1, and this is known as efficient circuit. B circuit is efficient, and this one is used very widely all over the world. I mean, why should you use an inefficient circuit? And in the third one, nothing else, simply for the circuit B, for the circuit in B, the Laplace transformed circuit has been shown in the C, as you can see it here. The Laplace transform is being shown. And yeah, I think you have understood the role of air gap or sphere gap, G. In fact, two standard sphere gaps of given dimensions were being used even for the measurement of very high voltages, because you would have a flashover at the same magnitude of the voltage applied. It may change when you change the type of voltage applied across. That is when you apply DC, positive polarity, negative polarity, you apply AC, you apply lightning, you apply switching. Again, the polarities of lightning and switching impulse. The the flash over or the background voltage would depend upon all these, and you can make a generalized table that for this type of voltage applied, for this size of the sphere, the breakdown would occur at this voltage for this gap distance. The tables are available. Tables were available, and to for decades, you can say, even centuries, you can say, for more than a century, that arrangement for the measurement went on. We'll talk maybe in more detail in the next chapter, number 8, of the measurement of high voltages. So that is the role of the gap, air gap, you can say. Now we will try to analyze this circuit. How does it produce the desired impulse wave shape of the voltage? Yeah, the energy rating of the impulse generator, energy rating of the impulse generator is given as the W is in watt, is given as 1 by 2 C1 U naught maximum square. U naught, there's a voltage applied at the charging capacitor C1, as we have learned in the previous slide, and the output voltage is given by the output voltage at the terminal, that means on the applied on the test object, will be given by in the Laplace form. Us is U naught upon S, Z2 by Z1 plus Z2. So yeah, when we talk about the energy rating of the impulse generator, if you want to increase the energy rating of a impulse voltage generator of certain level, say 1000 kV impulse voltage generator, so U naught would be fixed. How can you increase the energy level of the impulse voltage generator? Here, by increasing the charging capacitor. Higher W or higher energy level will be achieved for higher C1 of the higher C1. That means the higher energy level will be produced by the impulse generator when you increase C1. And when you test an object with higher capacitance, you need higher energy level also, because the current, the charging current by the test object at higher capacitance would be higher. So higher is the capacitance of the test object, higher energy level of the impulse generator is required at a given voltage and then you have to increase the charging capacitor value of the charging capacitor, which can increase the energy level generated by the impulse generator. I hope you get this point. Yeah? When we go to analysis, we are referring here to the circuit C, the Laplace transform circuit. Once again, I'm showing, and then we can write these equations. Us is equal to U naught by S, Z2 by Z1 plus Z2, and the capacitors we will learn what is exactly Z1 and Z2 are there, where Z1 is 1 by C1S plus R1, and Z2 is R2 by C2S upon R2 plus 1 by C2S, as you can see it here from the circuit. Once again, if, from the Laplace transform circuit, Z1 and Z2 are being defined. Z1, R1 and C1S. R1, C, then you can, at G, you can make a short circuit here. So R1 and C1 are forming Z1. And R2 and C2 in parallel are forming Z2. Yeah, R2 and C2 are in parallel are forming Z2. Then when you solve this, the following equation, here there is a slight mistake. No, fine, everything is fine. You get the equation like this, where the values of A and B are given here. Value of A will be this, and value of B will be this, and K is given as R1 C2 in this equation. The by substitution we find this, and quadratic equation S square plus AS plus B, where S square plus AS plus B, where A and B are given here, and the value of K is also can be worked out. And when you solve it further, from the transform table, the following expression in the time domain can be obtained, that the ut, that is the output voltage, ut small ut, this is the output voltage as we have shown it here. Ut, as you see in all these three, the output voltage will be given as ut is equal to u naught upon k, 1 by alpha 2 minus alpha 1, exponential of minus alpha 1 t minus exponential of alpha 2 t, as this is the equation, you get it. And alpha 1 and alpha 2 are the roots of the equation of quadratic equation S square plus AS plus B, and alpha 1 and alpha 2 can be given this way, as you can see. Alpha 1 and alpha 2 are being given here. Mind it, alpha 1 here in this equation, a by 2 minus plus under root of a by 2 square minus b. So alpha 1 will be minus and alpha 2 will be plus here. And yeah, every circuit has got its own efficiency. What is the efficiency of a circuit? It is in terms of energy, you can say. And energy is being converted into voltage here, because the current is not very significant over here. The voltage, current, there will be losses because of the current only, but what you get output is the voltage. So efficiency is U peak of the impulse voltage produced by U naught, the maximum magnitude of DC voltage with which you are charging it. And the efficiency can be given as also C2, C1 upon C1 plus C2, and is equal to 1 upon 1 plus C2 minus C1, isn't it? So if C2 for higher efficiency, what is desirable that the C2 should be smaller than C1, or C1 should be greater, much as greater as possible compared to C2. C1 should be as greater as possible. That will reduce the factor C2 by C1 to be smaller, and the efficiency will be more. So C1 should be much greater than the capacitors, that is the charging capacitor of the generator should be much greater than the capacitance offered by the test object. Now here's C1 is known to you. C2 you can always measure. So you can also estimate the efficiency is equal to 1 upon 1 plus C2 minus C2 upon C1. Okay. You can say this is also known as voltage efficiency. And what we are interested in is nothing but the voltage output. And just a minute. Yeah, we have also learned that the output voltage is a superposition of two exponential functions of the different signs. The only difference there is of different sign, as you can see it here. Yeah. Yeah. We will plot this output equation, the in the time domain, we can plot. Yeah, the superposition or of the two exponential part of the equation, we can plot it here as we see the when you plot the equation, this is the value of u naught by k alpha 2 minus alpha 1, and when you plot this here, the right hand side equation, that is alpha 2 t, you get the 1 by alpha 2 is a time constant. Similarly, 1 by alpha 1 is also a time constant. So the two parts will have two different time constants. And when you plot the total equation, the two parts of the total equation, it will look like this. So the resultant, you can imagine, will be the waveform as given up being given here, the resultant wave shape. This will be the resultant wave shape of the output voltage. So by plotting this, you can numerically also calculate what should be the wave shape, because you have an analytical equation depicting the total wave shape, and by the knowledge of the components in the network and the values of alpha 1 and alpha 2, you can determine the total wave shape, that means the wave front and the wave tail of the wave shape you want to produce. Time required by the voltage, that is voltage ut, to rise to its peak value. How will you find that? If you differentiate d u t by dt and make it equal to 0. You can get in this ut equation the time required to reach the peak value, and the time required to reach its peak value, let's call it to be t max, will be equal to ln alpha 2 minus alpha 1 upon alpha 2 minus alpha 1. This is alpha 2 minus alpha 1. So ln alpha 2 minus alpha 1, and the values of uh, alpha, wait a minute, we have defined alpha 1 and alpha 2, as you can see it here. So you can find out what will be the time required to reach the maximum value, and that T max is nothing but the wavefront time, isn't it? So that is how this can be defined. And when you make efficiency, efficiency in the terms of alpha 1 and alpha 2, you can also then calculate when you have the value. The efficiency will be equal to, you can say, alpha 2 by alpha 1 to the power alpha 2 by alpha 1, wait, no, I don't have it here, I'm getting slightly confused. Alpha 2, you have to have, I'll give you, don't worry, I'll give you exact value of efficiency in terms of alpha 1 and alpha 2. Let's not waste time here, and I'll give you that. Okay. Yeah. Then what you need is to uh, dimension the single stage impulse voltage generator. How can you dimension? That means what value of R1 and R2 you should take to produce a certain desired wave shape. That is nothing but dimensioning. As you can see it here, an impulse voltage generator circuit consists of capacitors and resistors only. And with an appropriate choice of the combination of the wave from the combination of the wave front and wave tail resistors, that is R1 and R2, desired shape of the output voltage, both lightning as well as switching switching impulse voltage can be produced. Yeah, what is the difference in lightning and switching impulse voltages? It is the difference in R1, the difference in wavefront and wave tail time. So desired shape can be produced by choosing the uh, shape you can say wave shaping resistors. R1 and R2 are nothing but wave shaping resistors. So R1 and R2 analytically, as you can see, are this value, and this is the R2 value, and both equations here for R1 and R2 contain the time constants 1 by alpha 1 and 1 by alpha 2, which determine the rise time and the tail time, which depend upon the desired wave shape. Now, some estimation work has been done for the time constants for some selected impulse voltage wave shapes have been worked out to be the time constants, that is your alpha 1 and 1 upon alpha 1 and 1 upon alpha 2 have been worked out. For the lightning impulse 1.2 by 50, the 1 upon alpha 1, that is the time constant uh, for T1, you can say, is 68.2 and in microseconds, and for 1 upon alpha 2 it is 0.405 microseconds. For the switching impulse voltage, the 1 by alpha 1 works out to be 2877 and 1 upon alpha 2 works out to be 104 microseconds. So these are the time constants values 1 by alpha 1 and 1 by alpha 2 worked out for the different wave shapes. If you put the values of 1 upon alpha 1 and 1 upon alpha 2 in your above equation R1 for R1 and R2, you can work the value of R1 and R2 for given uh, other constant, other what are the other components in the network? Nothing but the two capacitances, C1 and C2. C1 is fixed in the impulse voltage generator, but C2 may be different. So you can always measure the C2, that is the capacitance offered by a test object. And when with the knowledge of C1 and C2, C1 is fixed, always fixed in the is design. Is a design value. C1 is a design value of the impulse generator, and C2 is the capacitance of the test object, which can be measured. And 1 upon alpha 2 and 1 upon alpha 1 and 1 upon alpha 2 have been worked out. So for the desired shape, R1 and R2 can be calculated. What will you have to do? Suppose you have setting for you have an impulse generator. So when you work out R1 and R2, you change the resistor in the stage to the desired value as works out by these equations 1 and 2. And then the values for producing the switching impulse voltage wave shape R1 and R2 would be different. Then you change the R1 and R2 physically in the generator. You change the resistors of the desired value for producing the switching impulse voltage, and that is how it is done in the laboratory. That the same impulse voltage generator, you can use it for producing either lightning impulse wave shape or switching impulse wave shape as and when desired. The things become complicated when you go for higher voltage generation. That means the magnitude of the impulse voltage is desired to be generated very high. We like in AC power frequency generation, high voltage AC power frequency generation, we use here cascading of the circuits. We had voltage doubler circuit in DC. Here cascading of the number of circuits in series is done to add the output voltage. We learn about that in the next lecture. Okay, see you